All right. Good evening, everyone, and welcome. So glad to have you with us. I'm Nancy Waldrop, Vice Chair of Western North Carolina Sierra Club, and we're glad you're here for this great program we're getting ready to have this evening tonight, featuring Richard Wiener, who is here to talk with us about our mountains, the how and why they got here. And before getting started, one more thing. Okay, here we go. Before getting started with our mountain geology, we need to take a moment to say thank you to Ollie at UNCA for hosting our monthly programs and all the quality tech assistance that they provide so graciously. And it's Ollie's mission to promote opportunities to thrive in life's second half through programs of lifelong learning, leadership, community service, and research. Here we go. We just was stuck. Explore, enjoy, and protect the planet. This is the Sierra Club motto. When you join our local Sierra Club, you also join the National and State Sierra Club as well. As part of the National Sierra Club, you will receive a monthly magazine on national issues and projects. You will also be exposed to issues and opportunities at the state and local levels, learning about how the State Sierra Club, what their initiatives are, as well as being able to attend meetings locally with us and participating in the local Sierra Club projects. A very important local project is coming up and is critical to Sierra Club at both the state level and the Western North Carolina level as well. Arguably, this is the most important project we could participate in at this particular moment in time. And now Sierra Club member and secretary, Caitlin Constantine, will share more about this urgent project and how you can help. Caitlin?
Hi. Okay, let me go ahead. Do I move this over?
Yes. Oh, I'm sorry. Yes.
Okay, great. Hi, everybody. My name is Caitlin Constantine, and I'm the secretary of the Western North Carolina Sierra Club. I wanted to tell you all about a really important volunteer opportunity that's coming up. Happened yesterday. We are looking for volunteers to call Sierra Club voters. We need you to support 3 candidates in really critical races, and I'm going to give you a little bit of information about these candidates. Sorry, I lost my notes. Give me one moment. All right, so we are asking people to join us calling Sierra Club members. You can do this from home, phone banking from home. They make it super easy. They give you everything that you need. You're going to be calling Sierra Club members, not calling anybody who's going to be hostile. And I will tell you, as somebody who's been phone banking for other things, people are happy to hear from you right now. So strongly encourage you to get involved with doing this. So let me tell you about the candidates that the North Carolina Sierra Club is supporting. So they're supporting Rodney Sadler, Valeria Levy, and Representative Rodney D. Pierce, who's facing a tough challenge in the primary from former Representative Michael Ray, who's a longtime environmental adversary. The other 2, Sadler and Levy, they are running against Democratic lawmakers who sided with Duke Energy and Republicans to override Senate Bill 266 in July. So we definitely want to support the candidates that are running against these candidates because these candidates kind of sold us out. So we've got these opportunities to phone bank up here coming up Monday, February 9th and Monday, February 16th. From 6:30 to 8:30. If you use this QR code, it will take you to the sign-up sheet for Monday, February 9th, but you can also sign up for the shift for the 16th there. They will get you set up with everything. Like I said, you can do it from home. You're just going to make some phone calls and let people know about these races. These races are really important. Odds are good that they may not have heard about these races, and so you calling is going to be the first time that they're going to hear about these candidates. So it's really important that we start getting these people thinking about these candidates before they head to the polls, because the primary election starting February 12th. It's starting really soon, and we want to make sure that we get good candidates elected to go to the general election. Thank you.
Thank you, Caitlin. Question?
So, yep, got you. Dr. Rodney Sadler is running to represent NC House District 106 in Mecklenburg. Valeria Levy is running for NC House District 99, also in Mecklenburg. And then I do not have information about who where Representative Rodney Pierce is running, just that he's running against former Rep. Representative Michael Ray. Yeah. Yes. I do not have any information about endorsements for them.
Sierra Club isn't making any endorsements for city council in the primary. They most likely will be for the general election when it narrows down to 6 people. Okay? Yes.
Yeah. The endorsement cards? No.
We do not have any endorsement cards at this moment. Closer to the general election, we should be having those.
Thank you.
And please do take Caitlin up on that if at all possible, because it really is an important endeavor to get the candidates we need elected, even if they're not our candidates that would represent us. To get good candidates elected across the state is going to make a huge difference in what happens with North Carolina General Assembly. And probably can't be overstated how important that is at this moment. Okay. Change slides. It is our custom at Sierra Club to take a moment at each meeting to acknowledge with respect the land we are on today. Beneath our feet is the ancestral home of the Cherokee, and we want to thank them for protecting our forest and the environment for so many generations. And tonight, as always, and happily as always, we were afraid this wasn't going to happen this evening due to the snow, but it did. We are offering both the ability to enjoy our program in person here at the Reuter Center and in a Zoom format, as we do the first Wednesday of almost every month at 7 p.m. Also, each month prior to the program, we have a leaders meeting, which is open to anyone interested in helping us determine the future programs and other projects that Sierra Club undertakes. This meeting begins at 5 p.m. in the first classroom on the left when you walk in the doors on the upper floor, or either the first classroom at the top of the stairs. If you go up in the lobby, you'll see it right there in front of you. You may also join this meeting by Zoom as well if needed. And should you be interested, excuse me, in joining us, please contact Judy Maddox at judymaddox15@gmail.com, just so we'll know who's coming. And locally, our Kids Adventure Club, which is one of our greatest programs and outreach accomplishments, along with our monthly hikes, excuse me, are 2 of the favorite programs our local clubs that we offer to our local Sierra Club members. And now to tell you more about both of these activities is our Kids Adventure Club leader and one of our hike leaders as well, Ed Maggart.
Thanks, Nancy. Sierra Club has a national program called Inspiring Connections Outdoors to get kids out into nature and let them feel comfortable there and have great experiences and eventually want to help protect it. And in particular, we take all kids, but we're trying to connect with kids who don't have access to the outdoors for various reasons, or it's not part of their family's culture. We've got a couple of things on the horizon now. Theoretically, we were starting the Asheville Middle School in real life club once a week a couple of weeks ago, but between the ice storm and the snowstorm, we're finally starting next Monday, and we're going to have a group of 10 kids who've signed up for our Trailblazer Club that will be with us for 8 weeks in a row. So not only will they get to try some things outside, but we'll get to develop a relationship with them. This summer, we'll be working with some of the camps that are at city centers around Asheville. And for the first time, we're working with Asheville Parks and Rec. We may take some of those kids on an overnight camping trip. If you'd like to find out more about this, there's my email. I'm also on the website. And right now, we've had a number of folks in Adventure Kids Club who've moved or their lives have changed and they're not able to help us. So we always want more folks. We really need more volunteers who can come according to your own schedule and jump in and help us work with the kids. We also take adults out to explore and enjoy the wilderness. And I'm happy to say that there were 2 hike leaders, and within the last month, we've had a couple more folks train and now have done their provisional hikes. We have 4 different adult hike leaders. So we're working to have 2 or 3 hikes a month, some during the week, some on the weekends. Here are the ones that are coming up soon. A week from today, February 11th, I'm leading a hike at the Berea Trail System at Warren Wilson College. You can email me or look at the website. I've still got 3 or 4 spots left in that one. And that's a pretty easy hike. And then on Thursday, February 26th, David Reed is taking the Explorer Loop at Bent Creek in the National Forest, which is close by here. So both of those are kind of easy hikes and places that once you find out about them, you could easily go on your own. Then here's a weekend hike, the 28th of February. Amber Fox, another one of our new leaders, is taking a group to the Rattlesnake Lodge hike on Ox Creek. This one's kind of a moderate hike, about 4.5 miles. All of those are on the WNC website, so take a look and sign up, or feel free to reach out to me.
Thank you, Ed. And you really should try and join either one of those groups because it's a lot of fun. Now, this super flood slide, which was part of a discussion of Helene, the flood in Texas, and the flood in Spain, has been added tonight as Rich will be talking about our geology, which helped create Helene. And before we get into tonight's program, let's take a moment to add our March program to your calendar, as this will also be a most enlightening program. Hope in International Energy with Dot Sulak. Hope is certainly something that we all could use more of right now, and Dot Sulak, a well-known and much-loved Ollie instructor, as well as Sierra Club volunteer, is just the person to present it. Dot has unlimited energy herself, so this is sure to be a program that you will also enjoy. And now, have you ever wondered, even those of us who have lived here all of our lives, have you ever wondered just exactly how these mountains we call home got here? And what clues or proof was left behind, if possible, to unravel this mystery of the Southern Appalachians? Well, you are in luck, but because tonight, by taking us back 100 billion years ago and bringing us back up to the present, Richard Wiener is going to share that amazing evolution with you. Rich is a lifelong geologist with experience in university teaching, research, the petroleum industry. He received his BA from Colgate University and a master's in science and a PhD from the University of Massachusetts at Amherst. He has been teaching classes in geology, energy, and climate at Ollie on the UNCA campus since 2012. We will be taking questions at the end of Rich's presentation or at some point in the middle if he wishes to stop to do that. So for those of you who are here with us, please hold your questions until Rich asks for them or either the end of the program. But those on Zoom who are watching from home may put your questions in the chat box at any time. And we will answer those during the Q&A as well. So sit back, enjoy, and get your questions ready. Thank you so much, and it is now my pleasure to introduce to you Rich Wiener. Let's make him welcome.
Thank you, Nancy. I don't think I've ever had such a glorious introduction. Well, welcome everybody. I'm glad we could get out from the deep freeze we faced the last couple of days over the weekend and Monday and Tuesday. So it's good to see such a big crowd here. A little bit of a warning, some of the slides, people in the back, if you're squinting at all, there's some more seats up front, so you might see a little bit better. But let's see, let's just jump into it here. So what we're going to talk about today is Western North Carolina geology, and I consider it sort of a whirlwind tour of over 1 billion years of Earth history that affected our little corner of Western North Carolina. And to understand it, we've got to look at the big picture too. So we'll we'll zoom out to the whole Appalachian chain and we'll zoom out to the whole world in some places, but we'll also zoom down to the scale of a rock. And geologists can look at rocks like these that I've collected from Western North Carolina and tell a whole big story about them. And they're mostly correct. So at the break maybe, or at the end, I'll be glad to share what I know about these rocks that I collected. But for tonight, to try to distill what's usually about a 7 or 8 week class of 2 hours apiece down to 45 minutes, hopefully finished by 8. It was a struggle, so it's a lot harder to make a short presentation than a long one, especially for geologists, because we're really long-winded. So but I'll do my best. So I just picked a couple of highlight topics, and we've all been through the hurricane, or a lot of us who are at least been here for over a year. And so I thought I usually teach in Western North Carolina geology something about the topography, the mountains. And so what I want to do is tie that into what happened with a hurricane and how the mountains had a huge impact. And that, I think that'll be pretty clear to you. And then the second topic is just what is the bedrock of our state and where did it come from? Because 90% of North Carolina was not here at the beginning. It's all been added on later. So that's a story we're going to unravel in the last part, which is the whole plate tectonic evolution of North Carolina and the Appalachians over the last billion years. And it's quite an amazing story. So let's start out with a little bit about the topography and the hurricane. So what is topography? I'm going to get rid of this little, I didn't realize that was on the screen there. Topography is the study of Earth's surface features, including the elevation, the relief, and the three-dimensional shape of the Earth. So it's basically describing the shape of the Earth or the lay of the land, and helping us also to understand water flow hazards, because the water flow obviously is heavily influenced by the topography, not to mention the weather. And we'll talk about that in a minute. So if we look at this map here, this is a topographic map of the Southern Appalachians. Now, a lot of times you'll see topographic maps with contours of equal elevation. And if you've ever gone out hiking and used contour maps, those are readily available from the U.S. Geological Survey. I'm sure a lot of you have seen those and used them. But this is a kind of a color relief map, if you will, of the eastern United States showing the Southern Appalachians. And elevations on the scale on the right here are in meters. And so just for reference, 1,700 meters, a little over a mile. It's about 5576. So this kind of dark reddish brown color that you see in this part of the Blue Ridge in Western North Carolina, obviously this is the highest part of the Appalachians, the highest mountains east of the Rockies, of the Black Hills per se. And so here you can see very nicely outlined the Blue Ridge topographic province on here. So what are the other provinces around? So if we go from west to east, as we go into Kentucky and Tennessee, we have what's called the Appalachian Plateau Province, where we have a high plateau of horizontally layered sedimentary rocks that have been dissected by erosion into a dendritic kind of a drainage, elevations around 2,000 feet. And then we come to the east of there into what's called the Valley and Ridge, and we have spectacular, very long linear ridges and valleys made up of different rock types that have been folded, elevation about 1,000 feet, so a little lower. And then we come into the Blue Ridge, where the highest province of the Appalachians is, it's 4,000 to 6,600 feet, and average or 125 peaks over 5,000. Then we come east into the Piedmont, which is a lower relief area, 1,500 to 300 feet of rolling hills with occasional mountains sticking up out of there. And then the coastal plain, which is a very low relief area of 0 to 300 feet elevation of meandering rivers and swamps. And then in North Carolina, these three provinces, the Blue Ridge, the Piedmont, and the Coastal Plain, are separated by features, this one called the Blue Ridge Escarpment between the Blue Ridge and the Piedmont, and then this one called the Fall Line between the Piedmont and the Coastal Plain. And it's called the Fall Line because it's a line of waterfalls that goes from New York City to Georgia, and every major city from New York City south is on the fall line. So the geologic boundary set up where upstream navigation was stopped back in the 18th century, and settlements arose and mills were developed. And so a lot of our big cities are sitting right on this fall line. New York, Philadelphia, Baltimore, Washington, Richmond, down to Raleigh, etc. So these are the major topographic features of North Carolina and the Southern Appalachians. And now we're going to zoom in here on this little piece of Western North Carolina, and that's what we're seeing here. And you can see on the terrain map, the terrain view of Google Maps, you get a very graphic picture of how high the Blue Ridge is compared to the areas east and west. The Valley and Ridge sitting out here with these narrow, very long ridges of folded sandstone, and then the Piedmont out here, fairly low relief with occasional mountains popping up, and then the Blue Ridge here, which is 4,000 to 6,600 foot elevation. I tried to draft on here the state boundaries because they're really hard to see in Google Maps. So that's the Tennessee, North Carolina boundary, Georgia, and South Carolina, near Charlotte, Asheville for reference. And one of the things that's interesting about this is the edge of the Blue Ridge has enormous amount of relief, almost as big as what you get in the Rockies. People don't think of the Appalachians as major mountains, but right here, from Mount Mitchell to Old Fort, we drop 5,200 feet, almost a mile, in 11 miles. So in a very short distance, the elevation drops from over 6,600 feet to about 1,400 feet at Old Fort. And when you drive out Interstate 40 from Black Mountain to Old Fort and Marion, you go down that very long hill. That is called the Blue Ridge Escarpment. And the same thing happens when you go south towards Greenville on 26. The Blue Ridge Escarpment sits right here, just across the border in South Carolina, where you drop down to 1,000-foot elevation in Greenville from very high elevations here. And on the other side, Mount LeConte, I think it's around 6,500 feet, and Gatlinburg's about 1,300, maybe 6,600. Again, it's over 5,000 feet of relief in about 10 miles. And so both sides of Blue Ridge are very highly, very steep terrains. And this is because the whole Appalachians have been uplifted very recently in its geologic history. What we say about the Appalachians is that the rocks are old and the mountains are young. So the rocks I have here from the Appalachians, are anywhere from 1 billion to about 400 million years old. That's one with 9 zeros. And the uplift is in the last 10 million years. So that's about 1% of the age of the rocks. So to give you a little scale and time there. So these mountains were not this big always through their history. In fact, they were bigger at one time, then smaller, then bigger again. But anyway, moving along, what about the hurricane? So I put on here the path of the low pressure center from Hurricane Helene in this blue dashed line, and it didn't go over Asheville. But that was bad. It would have been better if it went right over us, because the worst side of the storm is going to be the dirty southeast quadrant, because it's a counterclockwise circulation. And so it's bringing up all that Gulf moisture as it rotates counterclockwise. So as a low pressure, say, was sitting right here in the Blue Ridge, the winds were whipping up from the south, carrying all that moisture from the Gulf of Mexico, and there was nothing to stop that moisture until it hit these mountains. So the Blue Ridge Escarpment became the first big mountain range that all the moisture from the hurricane hit as it came up into our area. And so the interaction of that tropical low and the counterclockwise circulation and the Blue Ridge topographic escarpment created a very heavy rainfall along the escarpment. I'll show you in a minute the rainfall totals, but they sit right above the Blue Ridge escarpment. They're not random. They're related to the topography and the path of the storm. And then what do we have in the Blue Ridge? We have narrow, confined valleys with vast drainage areas going from 5,000 feet down to 2,000 feet. And all that water pouring into these narrow valleys like the French Broad River, the Swananoa River, and it's got nowhere to go. It just piles up and eventually it runs into the Gulf of Mexico. But because of these high mountains, these valleys are constrained and the water is constrained, and it builds up and you get these very high flood levels. So the interaction of the tropical low and the Blue Ridge escarpment topography and these very narrow canyons that we have around here created a really catastrophic situation. So here's the weather system, how it's set up. We'll talk about the weather, the flooding, and then the debris flows in discussing a little bit about Hurricane Helene. I taught a 4-week class in it last fall. And so again, this is highly condensed. But here's the general setup. So on September 26th, the hurricane was off here. Here was the eye. It was in the Gulf of Mexico off Tampa. We were already getting, like, it's starting on the 24th. This was the third day of heavy rain before the hurricane actually came through here. This is what they call a predecessor event, predecessor rain event, or PRE. So as this hurricane circulated here, and it was by this time was a category 4, it drove all this moisture up through here with a counterclockwise circulation, and then it hit the mountains and dropped all the rain in here. And then that continued as the system moved north onto the land surface. And what set that up was there were 2 big pressure cells, the high pressure off Bermuda and the low pressure here in the interior, that funneled all this moisture up through here. And then there was a cold front that was stalled out here with a jet stream that also guided a lot of that moisture up into that area. And that moist air mass was driven upwards when it encountered the mountains, increasing the rainfall over the mountains as the air mass cooled, as it lifted due to orographic lift. So orographic lift happens when cold, moist air goes up a mountain or warm, moist air goes up a mountain and it cools, and cooler air cannot hold as much moisture as warmer air. And so it falls out. First is condensation and then rain. And so the elevation effect on that moisture causes it to rain where that high topographic boundary is. And so this was the weather system along the Blue Ridge escarpment that affected both the predecessor rain event for 3 days, and then on September 27th, the passage of the low pressure tropical storm through westernmost North Carolina and Tennessee. So here's a map of the rainfall, and I've drafted on here the Blue Ridge escarpment. You see Johnson City, Hickory, Asheville, Charlotte here, and then these colors represent rainfall in the red, and the pink represent higher rainfall amounts. So you can see here greater than 7, greater than 12, greater than 16 inches. And look at how it maps onto the Blue Ridge escarpment. So it wasn't heaviest in Asheville. It was heavy between Asheville and Hickory. And then, of course, the French Broad River, which runs north out of here, there wasn't as much rain up in Hot Springs and Marshall, but all that water went up there because it was in the river coming from the area east of Asheville where the heaviest rain was. So this is not an isolated event, though. There have been tropical storms These are just the ones that went through Asheville. If you put all the ones that went through North Carolina, you have a spaghetti map, basically. You got storms coming all which way. And this is only since 1950. But we've had three really major floods in the last 100 years, 110 years, I guess, going back to the hurricane in 1916, which dropped 22 inches of rain in Asheville and rose the French Broad 23 feet. The 2004 double whammy hurricane of Ivan and Francis came through, dropped 30 inches of rain in places and 20-foot of elevation of the French Broad, and then Helene, which maximum rainfall was 30 inches up on Mount Mitchell, actually, and a 25-foot river elevation above normal. So if we look at the 1916 flood, there's pictures from the damage of it here. And then jumping up to 2004, this is Biltmore Village. You could have taken this picture in Hurricane Helene and you wouldn't be able to tell the difference. It was pretty similar. But there was more widespread flooding and more debris flows in Hurricane Helene than there was in this one. But there's a picture much like that from Hurricane Helene. So we know that the rainfall was, the rainfall was set up by the Blue Ridge Escarpment and the passage of the low. I'm not going to show you a lot about the flooding because I'm sure you've all seen pictures and videos, and I've got a whole bunch of stuff. I got one picture on the flooding, the French Broad River. We know the Swannanoa flooded. There was flooding in Marshall. There was flooding in Chimney Rock, everywhere. Black Mountain. But the other thing that happened that people are maybe less aware of, you might have heard of it, are debris flows. This is a type of landslide. And here's a picture of one that's 3/4 of a mile long and basically wipes out everything in its path. I went up the Blue Ridge Parkway in September of this year after they finally opened that section up to Craggy Gardens. And there were two massive landslides there that I saw. I've got pictures of them. I didn't put them in here, that occurred in that area too. But so what is a debris flow? Debris flow, easy for me to say. It's a landslide in which soil, rock, debris, and water flow down slope at speeds up to 35 miles an hour over long distances, and they can carry very large objects, boulders, trees, cars, houses, potentially destroy everything in their path with little warning. And here's the thing, here's the warning for people, is that 5 inches of rain in 24 hours is a trigger for debris flows. Now, they can occur with less rain than that too, but if you have 5 inches in 24 hours, you're almost guaranteed to have some debris flows somewhere. There were over 2,000 debris flows in Hurricane Helene, and 1,000 of them were what they call significant, that had loss of life, property, or infrastructure. So the steepness of the slope, the soil saturation, the bedrock type and orientation all play a role also. But here are the landslides or debris flows from Hurricane Helene, and see where Asheville is and Hickory. Again, it's along that Blue Ridge Escarpment. That's where the heaviest rain fell. And it's also where there's a lot of steep topography. So that's another factor that goes into debris flows. So I'm going to show you the Google Earth images from Garin Creek, also known as Craigtown, where 13 people died. I'm sure you heard about this one. It's down south of Fairview. Sorry, my computer's got a mind of its own. So here is the Google Earth image of the Garin Creek community with a fire station here and the roads before the hurricane. And this is the post-hurricane view. And look at these brown patches through here. Those are the debris flows that came down during Hurricane Helene. This is an October 2024 satellite image. There's some really good videos by this geologist, Philip Prince, about this event, which I would recommend you get on YouTube. It's something called GeoModels. You can look it up. And then if we zoom in on this, well, here are these debris flows. I guess you can see them. They're pretty obvious. If we zoom in on Guerin Creek area, here's the before. You can see the community there with the fire station, the roads. You can see some houses in here, farmland. And then this is what happened afterwards. There's the debris flow that came right through the town. There's the fire station that you can see in this image. There's that road coming through right there. Here's this road coming down at an angle like that. So this whole area right in through here basically got wiped out with the homes and the people in them. And there was a sad story about a fireman that went in to rescue somebody from one of the homes and got caught up in a second debris flow. And he and I think it was his son or his nephew, passed away. But there was that debris flow. And about a third of the deaths from the hurricane were from debris flows. Most of the rest were from flooding. But okay, that's all I've got to say about the hurricane. There's a lot more about it, obviously. So the next topic I want to hit was about looking at our bedrock. So it's a complete change of pace here. So what can we learn from the rocks to understand the history of Western North Carolina, how it got to where it is today and what it looked like in the past? And so to do that, I'm going to just run from west to east across the state and describe the rocks and their ages. Maybe it's a little bit dry, but it sets the stage for some really exciting plate tectonic stuff that comes after it. So first you have to know the three types of rocks. Okay, who knows? Sedimentary, deposited by water, wind, and ice. Igneous, crystallized from magma, either underground like a granite or above ground like a lava flow. And metamorphic rocks are modified by pressure and temperature and deformation. They're usually folded, like this road cut on 240 by Bocaccia Ridge. You can see the folds in there. And here's a Stone Mountain granite. That's a close-up of the grains in a granite, quartz, feldspar, and mica. And a sandstone with beautiful horizontal layering here deposited on a beach 520 million years ago when it was the shoreline. So where are the North Carolina rocks? Here's a geologic map, very simplified, of North Carolina. We'll start in the Tennessee Valley and Ridge, go through the Blue Ridge, the Piedmont, the Carolina Slate Belt, and the Mesozoic basins around Durham, and then the coastal plain. And they generally get younger from west to east. The Blue Ridge is over 1 billion years old. The coastal plain sediments are anywhere from 100 million years old to very recent. So starting in the west, here's the Tennessee Valley and Ridge, and I hope to make a couple of these slides a little bit interesting for you. This is a big syncline or downfold in a limestone along Interstate 26, just outside of Kingsport, Tennessee. You can drive up drive up 26 for about an hour and you'll get here and you'll see this syncline and a big anticline next to it on the side of the interstate. And this was deposited about almost 500 million years ago in a very shallow sea, like a coral reef. And then it was folded much later when Gondwanaland, which was Africa and other continents, collided with North America. And the collision was off what's today in the offshore, but the stress transmitted all the way across the entire state of North Carolina, all the way to Tennessee, and folded these rocks. Amazing story. So now we're moving from west to east. We go from the younger rocks of the Valley and Ridge into the oldest rocks and the hardest rocks in the Blue Ridge that make up the high mountains of the Blue Ridge. And this is the mile marker 5 on Interstate 26. If you go close to the Tennessee line, there are a bunch of really big road cuts through these rocks that make up the core of the Blue Ridge. These are 1 billion years old, 1,100 million years old. Metamorphic rocks, deformed, and at high temperatures and pressures, temperatures around 800 degrees Celsius, 1600 Fahrenheit, and about 8 kilobars, about 25 to 30 kilometers deep. So this was in the core of a continent-continent collision. If you could drill down through the Himalayas today, about 30 kilometers, these are the rocks you would find, these kind of rocks. Very high temperatures and pressures. And then also in the Blue Ridge, on top of these very deep metamorphic rocks, you have these sedimentary rocks that were deposited at the surface with these little blue quartz chips that came out of these gneisses and were deposited in these very coarse sandstones and conglomerates. This is from the Smoky Mountain National Park at Clingman's Dome. This is actually from the parking lot at Clingman's Dome. And look at the rocks there, this photograph. And you can see this is a sediment which is made up of material that broken down rocks that were deposited in a coarse gravelly stream. So moving to the east into the Piedmont, we come across very high temperature pressure gneisses again. This is from the UNCA Botanical Gardens. If you walk down along the river and you look to your right, you'll find this rock, and you can see my pen there for scale. So this is a pretty neat fold. So how does a hard rock fold like that? Well, it gets so close to its melting temperature that it gets soft and weak. And there's actually some granite in here too. This white rock in here, it got hot enough to melt. So this got really hot, and some of it melted and made some igneous rock, this granite here. And then obviously the pressures of this collision that happened caused great folding in the rocks as well. So it's a really pretty outcrop actually that you can see down there. What else is in the Piedmont? Well, we have these rocks. I'm going to go grab one of them. And I know not everybody can see these, but let's see. Maybe this is a good one. Maybe y'all can see that shiny thing. That's a big piece of mica. So this is from Spruce Pine, North Carolina. And the other rock, the other minerals in here, this gray stuff is quartz, and the white stuff is feldspar. So this is a granite, but with really big crystals in it, not a granite like this one from Mount Airy, which is a typical kind of way a granite looks, little salt and pepper color to it. So what's interesting about that is that this computer and all your cell phones are made up of the quartz that came out of that rock. All the silicon chips in the world today are made from spruce pine quartz because it's 30 parts per billion in purity. It's very high purity. And it's mined up there in spruce pine by a Norwegian company owns the mine and processed. And it's a complicated process, but basically because of the high purity, it's a really good conductor. And that's why it's used for cell phones and tablets, computers, televisions, and every other place that we have computers. So a little piece of important resource from North Carolina. And the other, and we have those kind of granites with the big crystals. And then we have the more normal looking granites like Looking Glass, which looks like that other rock that's just kind of small pieces of quartz and feldspar. So that's the Piedmont. Granite and metamorphic rock like gneiss. So now we cross into the Carolina Slate Belt east of Charlotte, and we see some completely different kind of rocks. These are, instead of really high temperature and pressure rocks, these are very low temperature and pressure rocks, quartzites and slates and conglomerates. And you can still see fossils in these rocks. And here's a trilobite from the Cambrian that's been deformed a little bit. And what's interesting about this trilobite that's located here east of Charlotte is it's completely different from the trilobites that you would find in Tennessee. And that's because it was formed in a completely different world. It was offshore Africa in a completely separate continent at the time. If we look at North American trilobites and trilobites from the Carolina Slate Belt and places in eastern Newfoundland and Massachusetts, those all have African affinity. And they tell us that there was a vast ocean between western North Carolina and what's now the rest of North Carolina, which was at that point on another side of the ocean. And there's also gold in the Carolina Slate Belt. North Carolina was the #1 producing gold province in the country until 1849, which is when California gold rush started. But there were $5 gold coins minted in Charlotte in the 1800s. And here's a gold nugget. The first piece of gold was found by a 12-year-old boy in a stream. He pulled this big rock out and they used it for a doorstep. And it turned out it was a 17-pound gold nugget. So that was the beginning of the gold rush. That was like 1799. And here's the gold in the volcanic rocks of the Carolina Slate Belt, which is where it occurs. Okay, so moving further east to the Durham area, we have these green basins here. These are much younger. They're Mesozoic, Triassic, and Jurassic, 240 to 180 million years old. And they consist of sedimentary rocks and basaltic lava flows and basaltic dikes. And here is a rock called diabase, which is a type of basalt at the Museum of Life and Science, where my daughter works and is displaying the big igneous rock there with her children. And also in those basins, we have conglomerates and sandstones that were deposited in streams coming off of Rift Valley mountains. And dinosaur footprints in the Dan River Basin that runs into Virginia. Here's a theropod dinosaur footprint from the Dan River area near the Virginia boundary. Of course, you wouldn't have those in any of the other rocks because there were no dinosaurs in the Paleozoic. And then we go to the coastal plain to the next geologic era, to the Cenozoic, and we just have sedimentary rocks here, sandstones and shales. And in Aurora, North Carolina, which is near the coast, we have these beautiful marine fossils and phosphate pits that have been discovered from the Eocene to the Pliocene from about 56 to about 5 million years ago. And also there were mastodons here, but not in North Carolina. This one's from the Florida coastal plain. This coastal plain runs all the way down to Florida. So this was a place where we have the Cenozoic megafauna, if you will. So last bit on the bedrock is this is going to be set the stage for looking at the paleogeographic maps in the next slide. I got that itchy trigger finger, sorry. So if we look at this geologic map again, these red lines are sutures. So the areas to the east of this suture were not here before 470 million years ago, but these are land masses that came in and collided with North America back in the Ordovician 470 million years ago. And then this whole area, like the Carolina Slate Belt with its African trilobites, it was also separated by a vast ocean from North America, and it collided about 400 million years ago. So at the 470 to a billion years ago, this was the edge of North America. The rest of this place of North Carolina that we know about wasn't here, but it all came in later. So I said I'd take questions now, but I think I'm going to just plow through, if you don't mind, and I will, let's just take them to the end, because I got the momentum going and I got to get through this stuff. So, okay, the plate tectonics story of North Carolina and the Appalachians, just in case you don't know, you probably all heard this. This is a scientific theory describing large-scale motions of lithosphere, which is the outer shell of the Earth. It's brittle. North American plate, for example, goes from Iceland all the way over to the old Soviet Union, to Eastern Russia here, and from the northern tip of Greenland to the northern Caribbean. So that's one plate, and includes a continental piece, which is the North American continental crust, and an oceanic piece. And Eurasia, includes this Eastern Atlantic plus all the rest of Eurasia. So, and we look in cross section through the whole Earth, from the center of the Earth out to the surface here, we see the layering of the metallic liquid outer core and the solid iron inner core, and then the rocks of the mantle and the crust and the lithosphere here. And then the mantle is so close to its melting temperature that it circulates or convects due to the heat. And as those convection cells rise, they spread apart in the middle of the ocean to make a mid-ocean ridge, and that creates seafloor spreading. And then those oceanic lithospheric plates subduct under continents in a subduction zone. And those are the major types of plate boundaries. This is a picture of ice on water, and you can think of the hard rock lithosphere riding on the soft ductile asthenosphere as ice on water. Although the asthenosphere has a little more strength than water, but it's kind of a good analogy. And then we have three types of plate boundaries. The spreading center, which you can see in this animation, is where the magma comes up and pushes the plates apart and they move laterally. And then the convergent subduction zone, where the oceanic crust subducts underneath a continent. You can see in this animation here, you get melting, you get a line of volcanoes, you get a line of devastating earthquakes and tsunami, all associated with these convergent margins. And then the third type is the transform side-by-side movement here that you get in places like the San Andreas Fault, for example. So now cast your mind back 1 billion years, actually 1,100 million years, to the first supercontinent. We have two supercontinents. We're going to do the story now from 1,100 million years to zero. There are two supercontinents, and then they break up, and that's the big picture. So the first one here is Rodinia, it's called. And this is one landmass with one universal ocean. So all these little components here, they weren't separate. They were all together into one big landmass. But we recognize them today as separate entities, so they're labeled. You know, Siberia, North America. North America, by the way, is tilted on its side 90 degrees with the equator running through it. And Greenland, for example, is here. Mexico is here. So the whole North American continent's rotated 90 degrees at this point in time, and it's through the future, it will rotate to its current position, which you will see in the movie. So North Carolina would sit right here on the east coast of North America. Present day North is up this way. Paleo North is this way. And so what happened 1,100 million years ago? Well, all these pieces came together and made a gigantic mountain belt. This would have been like one giant Himalayan mountain belt that went all the way around the world in this area that's now colored orange. And those rocks are in the Blue Ridge Mountains of North Carolina and Tennessee. So these rocks sit right here where these continents collided. As I said, they would, if you drill down 30 kilometers in the Himalayas today, you get rocks like these. And then the next thing that happened is the continents started to break apart. And this is what happens later, too, with Pangea. And this is the zone of rifting, which didn't completely follow the zone of collision. Here's the collision zone. And then the stipple pattern is the rifting zone. But in North Carolina, it just pretty much followed right along. And gosh, we can see those rocks right here. Across the Tennessee line, about 3 miles on Interstate 26, you see this black rock here. It's called a gabbro. This is a basalt that formed as the continent started to rift apart, like East Africa is rifting apart today and making the East African rift system with the lakes and the volcanoes like Mount Kilimanjaro. These are the magmas that came up as Rodinia started to break apart, and they intruded into the Blue Ridge gneisses that we see here that formed during the collision. So they're in the same place as you can see here. They overlap each other. So then if we move forward to 550 million years, we went from one supercontinent into three supercontinents. So this is Gondwana, this is Laurentia, and this is Baltica. So Laurentia is North America, basically. There's Hudson's Bay and Greenland over here. There's North Carolina. Mexico's down here, Siberia. Here's Northern Europe, and this is all the southern continents, South America, Africa, Antarctica, Australia, and India. And in between, we have an ocean forming, because to break up continents, you have to form an ocean with a spreading center in between, like we have in the Atlantic today, and that was called Iapetus. And these continents drifted apart. And notice that North America is still tilted on its side, with north up in this direction, but paleo north was that way. The equator went right through this section of North America. Now we're going to, all the next slides, we're going to do a 90-degree rotation. So do a mind shift here, and we're going to look at all of them with North America fixed north, so it'll be a lot easier to follow. Here, so there's US-Canada border. So this is sort of like what we're used to, but North Carolina is just a little sliver here. Remember I said 90% of it wasn't even here at the time. So here we go, USA, Canada, Greenland, Europe, and Africa, and the rest of Gondwana. So these maps show highlands, lowlands, shallow marine on the coast, and then deep marine in these colors, paleogeography being the study of historical geography or the past physical landscapes. So here are the three continents that Rodinia rifted into. That's the edge of North America there, which is going to be the site of the future Appalachians that run all the way from Alabama to Norway. So the whole Caledonian mountain belt from Norway to Scotland to Wales to East Greenland, it's all part of the Appalachians, but it's just been moved across by the Atlantic Ocean. And there was a seafloor spreading center here that separated all these continents, Europe, Africa, Gondwana, and Laurentia. Paleo equator is still over here. We're actually in the southern hemisphere at this time. Here's the paleo north. And North Carolina is kind of spread out all the way from Africa to North Carolina today. So I've kind of got these reference points in here so you can see what happens. So the next thing that happens is you go from just a divergent margin, you develop a convergent margin with a volcanic arc. And here's that volcanic arc offshore of North America. And so this is the Laurentian, or the Blue Ridge would be along here, the Piedmont here, and then the Carolina Slate Belt would be out here, and Gondwana out there. And again, the future Appalachians, and here is a subduction zone where you have a convergent margin. So if you look at a cross section across North Carolina, you'd see the North American continent, you'd see a narrow Iapetus Ocean, you'd see a subduction zone and a volcanic arc. And that's what we're seeing there. And North Carolina is really spread out. Charlotte went way out here. Now it's back, back here somewhere. So as we move forward in time from this one to this one, now this volcanic arc is going to collide with North America, and this is going to create what's called a tectonic orogeny. And orogeny is a mountain building period. The tectonic orogeny is the collision of the tectonic volcanic arc with Laurentia, or North America, and that collision created all those big folds that I'm showing you in the botanical gardens, and they were created in this collision zone. And if we move forward in time now to the Silurian, we have another orogeny here called the Cherokee. This is only in the southern Appalachians. It doesn't occur up further north. And then we have Baltica here getting ready to collide with North America, and another microcontinent called Avalon. And that's going to make some more mountain building. So the Caledonian orogeny is typified by the deformation in Norway and Scotland, the Caledonides of Scotland and Wales, and eastern Greenland. And that's when Baltica collided with North America in the Silurian period. And then after that, we have Avalon colliding with North America, and that makes the Acadian orogeny, named for Acadia National Park in Maine. which has all these granites that formed during this continental collision. So one microcontinent or continent after another colliding with North America is kind of the story here. And then finally, when we go from the Akkadian orogeny to the end of the Paleozoic era, we create Pangaea, and the Theic and the Rheic oceans that are out here are gone, and Gondwana collides with Laurentia, and now we have one supercontinent again. And we have high Appalachian mountains like the Himalayas today. This was a big continent-continent collision, which we think is similar to what happens when India collides with Asia. And now everything's back to kind of where it is today, from being all spread out. So the next thing that happens is we rift the continent apart in the Triassic, just like we rifted it in the 750 million year event. We make these rift valleys, and we create the Durham Basin, the dinosaur footprints, and this would be like the East African Rift today. This is a picture of what happens after the Triassic. As seafloor starts to spread in the Atlantic and North America, Africa, South Europe, and South America all start to form as individual continents. They were all one before this. And that's how that went. And subsequently, we're going back to the beginning of that. So the first little thing that happened was we got a narrow ocean basin here between North America and Africa in the early Jurassic, and we have marine sediments in here that tell us this. And from this map here, which, let's see if I can get this to the end, these colors are the age of oceanic crust. So the red in the middle is present day, and the blue on the outside is about 170 million years old. And so it's symmetrical. And so at 170, we just have the very first little bit of oceanic crust forming on a spreading center. And there's that spreading center that became the Mid-Atlantic Ridge. And the analog to that is the Red Sea today. It's a 10 million year old ocean basin separating the Arabian plate and the African plate. And then the rest of the story is pretty simple. It's just more and more spreading, more and more continental separation. We see here in the late Jurassic, the central North Atlantic forming the Gulf of Mexico. The South Atlantic hasn't formed yet. It's going to wait till the Cretaceous to get going. Europe is still tied to Greenland, to North America. None of these basins have opened up yet. And now we're starting to propagate that mid-ocean ridge spreading center between Greenland and North America and Greenland and Europe as they start to separate in the late Cretaceous. And this is a time of the highest sea level in Earth history. And you can see the western interior of Canada and the United States was connected to the Gulf of Mexico. The Arctic and the Gulf of Mexico were connected by a seaway. There were marine creatures inhabiting Colorado and Wyoming, New Mexico, Montana, Alberta, all the way up to the Arctic during this time period. And then jumping all the way forward to 1 million years ago, during the last ice age, we have continental ice down to New York and across into the Midwest, over Greenland, where it still is today, and over continental Europe in the northern piece. And the spreading now propagating all the way up into the Arctic Ocean, and the Atlantic Ridge has now propagated up into the Arctic. And the analog for this ice sheet would be Antarctica today, about probably 2 miles thick here. And then today we see the Mid-Atlantic Ridge continuing to spread, the Arctic spreading. North America's moving away from Europe and Africa about 2 centimeters a year, every day, every year. And it all keeps going. And I'll show you this movie and then we'll take some questions, because this is really worth watching. I had to save the best for last. 540 million years ago to present. The little red dot is Chicago. This is North America turned sideways. This is Gondwanaland, Baltica, or Siberian Baltica. This is now the Ice Age in the Ordovician, an extinction, the tectonic orogeny, Caledonian orogeny, the Akkadian orogeny, and now the Alleghanian orogeny, which is the culmination of Pangea forming, and the big southern continental ice sheet will develop. This is called Tethys out here. It will disappear. The Atlantic's going to form in here. There's Chicago. This is all little plates in China that are colliding. Now, the Atlantic's going to start breaking up here and then heading north. And now Madagascar, Australia, and India will start to separate from Africa. The South Atlantic will open. Oh, it's loud. Here comes India. Did you see the Ice Age at the end? Just the very last piece. The last one. So those are the three highlights from the geology of North Carolina, and you know, it's not just North Carolina, but to understand North Carolina, you got to look at the whole world, especially the Southern Appalachians. So here are a couple takeaways. The Blue Ridge Escarpment played a major role in rainfall, flooding, and debris flows during the hurricane. The bedrock on North Carolina spans 1,100 million years. The eastern 9/10 of North Carolina is exotic to North America, was not here originally, and the paleogeographic history is complex and beautiful, including rifting, spreading, marine flooding, volcanic activity, Himalayan scale mountains, and recent uplift, which I didn't really talk about. So thank you.
Thank you very much, Rich. That was an enlightening display all the way around. Thank you. Thank you again. And now we will take questions from chat and in the room. And if you have a question in the room, either Ed or Dave will, not Ed, excuse me, Steve or Dave Erb will be around with a microphone. Please do wait for the microphone because the people on Zoom can't hear the questions if you don't have the microphone. So we would just ask you to do that and ask away. Thank you.
We can go either way. Well, I guess we could start in the room. That's the way I usually do it.
Oh, you don't have one? Okay.
Okay, go ahead.
I remember last year, the Sierra Club had a video, a movie that was talking about the geography of Western North Carolina in relation to the hurricane and how that all, do you guys have that? Do you know what I'm talking about?
I'm not sure.
It was at a Sierra Club meeting about a year ago. Okay.
And what was it? It had the, oh. There might have been one of those Phil Prince geomodel YouTube videos. He's done a great job with the hurricane, and yeah, just go on YouTube and look up Phil Prince and Hurricane Helene, and he's got things on the flooding, he's got things on the debris flows, on the weather systems. But I'm not sure what you're referring to because I'm not aware of it.
So I just wanted to say that we have recordings of all of our previous programs on our website. If you go to our website and then you look on the right side at the top of the column, you'll see recordings of past programs. All of our recordings of past programs are there.
Go ahead.
Hi, I've taken your class before and they're just great, little slower pace. And you talked about how high the Blue Ridge Mountains had been at their highest peak. I wonder if you could remind us what that was.
Yeah, so we really don't know how high they were at the highest, but the inference geologists will use the present as a key to the past. That's kind of a guiding principle. And so because Pangea was a continent-continent collision, we look at the type example from today, which is the Himalayas. And with those kind of elevations, 20 to 29,000 feet, we suspect that the Appalachians might have been 25,000 or so feet. We don't know the number, but in some of my classes, I've also talked quite a bit about the whole uplift history because, after that period, there was a period of degradation and erosion, and then there were 3 more periods of uplift, but nothing like what happened from the continent-continent collision. You get higher mountains from a big plate collision like in the Asia Himalayan collision than you do from the other mechanisms that caused uplift more recently, which are somewhat obscure really because they're not necessarily plate related. But what we think is that the North American plate is getting pushed from the mid-Atlantic ridge to the west because of the spreading. And it's running up against a backstop in Western North America, which is the Cascadia subduction zone, the San Andreas Fault, and the Mid-America Trench. And so the continent is squeezing. And if you look at drill holes in the eastern United States right now, they're under compression. And so that's what causes our earthquakes, by the way. And that's also probably what's causing the uplift more recently that makes our mountains here so high and beautiful.
I got some questions. I actually have 2 people who want to hear more about the recent uplift. Nan and David both asked you to explain more about the recent uplift.
And I just did, actually.
Oh, so if there's anything else you want to add, otherwise we'll move on.
Let's see. I have slides that talk about it, and I could get one up here, but why don't I do that while we answer another question, maybe?
All right, I have another question for
Okay.
you. From BB. So the Appalachians were as tall as present-day Himalayas. Was it weathering that made them less tall?
Yeah, over time, the Himalayas are still going up. India has been colliding with Asia for 50 million years. Why? Okay, well, if you look at this, I'll show you why. I think I will. Okay, so I don't know, you can't really see it on here, but I'm going to freeze it. So there's a spreading center that runs down here and runs down through here and runs through here, and it's pushing India north. That's still spreading. And so the point is, India is still pushing northward because it's being pushed by the spreading center behind it. And so it's been colliding for 50 million years and it's still going up. So I'm sorry, I lost my train of thought. What was the question about again?
The question is about weathering that made the
The weather.
Appalachian. Yeah.
Right. So those mountains are being tectonically uplifted, and so they will stay high as long as that tectonic force is there. But once that tectonic situation changes, plates rearrange or whatever, erosion is going to take over, and it's going to start stripping away, eroding away the top, and there won't be that upward force that we have today. And so what happens, you can actually run a calculation and figure out that if you take the Appalachians to about 25,000 feet, in about 70 million years, they should be reduced to sea level. And so the reason they're not is that there've been renewed uplift over time. So hopefully that answers some of that.
A question, when you showed that ridge of volcanoes and land that was pushing off Carolina and eventually got pushed into that, is that a subduction-like event, or do volcanoes form from something else?
Yes, that's a subduction event. I think you're referring to this.
Yeah.
This volcanic island arc. Is that what you're referring to?
Yeah.
Yeah. So look at this cross section here. So here's North American. This is in depth. And here's this volcanic arc, which is this thing right here. So there's a subduction zone. That's what this yellow line indicates. That's the trench where the subduction, that's the plate boundary, where the Laurentian plate is subducting under this volcanic arc, which is a separate plate. It does. And that's what happens when Iapetus closes in the next slide right here. And I have cross sections that show that. But this gets thrust up onto the continent, actually, is what happens is these approach each other. And the subduction zone, this arc, volcanic arc, actually gets thrust up on top of it. And the Brevard Fault that runs down through Brevard is actually a trace of that fault. Along 280 is that's actually where that happened in the Ordovician. You can't see it now. It's all covered with, you know, soil and sand and stuff. But underneath there, that's where that collision happened. And I've got a whole series of these cross sections that show that. It's kind of a cool story. And what happens is you get thrust faults. And then the other thing that happened in that event is this is a piece of the mantle that exists in Western North Carolina that was coming from this this black material here got pushed up on the continent, and actually this is a piece of mantle. You'd ordinarily have to drill 30 kilometers down to find this. But in a collision zone, sometimes piece of that mantle will be thrust up on the continent. This is a rock called dunite. It's made out of olivine, and it's green for the mineral olivine, which is also peridot. You may have heard of that.
Is also the muddy French Broad River eroding as the pressure is coming up? The French Broad River's job is to wash away. So I don't know who's going to win, but it's a billion. Is that the oldest 1 billion years old river?
The river? No, it's not 1 billion years old, but I was putting something together for this Appalachian geology, and I wanted to go look and find a slide about that. It's the age of the French Broad River, and it was something new for me that I hadn't really. So let's see, it's under. I guess it's here. Yeah, it's in this slideshow. So I'm gonna find it and try to answer your question. It's a long slideshow, wait a minute. Like a lot of mine. Okay. Oh, by the way, this is a story of. Just hold on a second. I'll get there. Okay, here we go. Here's the French Broad River Basin right here. Flows the Gulf of Mexico. Here's Asheville, Marshall. This is the Broad River, which, flooded Chimney Rock and Lake Lure, Continental Divide. So the French Broad River, what's interesting, it flows northwest across the hardest rocks and the highest mountains of the Appalachians. Those Blue Ridge metamorphic rocks that formed 1 billion years ago. Why in the heck would a river flow up across the highest part of the mountains unless it's older than the uplift of those mountains? And that's one of the reasons we think the uplift is young and the river is old. Because if you just take the topography today, take the Blue Ridge, the highest part, the Piedmont, and the Valiant Ridge, and you start draining off of it, everything is going to drain away from the highest part. But the French Broad River cuts across. It goes from down south of Hendersonville through Asheville, Marshall, and then meets up in Tennessee around Newport and runs eventually into the Tennessee River, the Ohio River, and the Mississippi River in the Gulf of Mexico. So it's going across the highest part of the Appalachians. And so this is one argument that the river is actually older than the Alleghanian orogeny, which is 270 million years old, because that's what really elevated the Blue Ridge Mountains and brought them up in a big thrust fault. And so, you know, you maybe have heard about the French Broad River being one of the oldest rivers in the world. Well, this is the evidence for it, that it's that these mountains, these big thrust faults, were formed about 270 million years ago. And if the river was younger than that, it wouldn't go across them because it would have been too hard. I mean, water is not trying to do the hardest job, it's trying to do the easiest job it can. And so it was there before those mountains came up during that final collision that created Pangea. Okay.
I have one more question.
Okay.
This is from Nancy Davis. She says, thank you, by the way. Lots of people online, thank you for this. And she asks if you can suggest some more reading that that people might want to explore in order to find out more about this topic.
So the book I recommend in my Geology of North Carolina class is Carolina Geology, I believe. And some of you have told me, I've got some people out here who've been in some of my classes, and some of you have told me that that I think it's called Carolina Geology. And it's written by Kevin Stewart, who is an emeritus professor at UNC Chapel Hill in geology, structural geology. It's really well written. He has a co-author who knows how to make science understandable to the public. And that's pretty important characteristic, which, you know, I realize I don't always get that right. And so anyway, it's very readable. And the first third of the book is a description of the general geology and the plate tectonics and a little bit of the history. The last 2/3 is the geology of all the state and national parks in North and South Carolina. So if you like to travel and hike, you go to Stone Mountain, Mount Airy, the Great Smoky Mountain National Park. In South Carolina, there's some really great places, Caesar's Head, Table Mountain. You know, he's got descriptions of all these places. Triple Falls and Hooker Falls, all that whole DuPont Forest area. And so I'd recommend that book. Yeah.
Would it be possible for you to explain how scientists aggregate the data that was necessary to come up with the animation that we showed of over billions of years?
Yeah, that's obviously it's a very involved process, but for the last 200 million years, the basic technique is captured in, what's that movie? Here we go. And I'll put this on the screen so the Zoom people can see it. Here is taking the continents and using the age of oceanic crust to run. Now it's running forward in time, but the way you would do this is you run backward in time. You start with, so you start with this information here, and then you take these land masses and you match up the ages that are similar on the same side. So you match that blue with that blue and that yellow with that yellow. And when you match them up at the middle, that brings the continents back. So that part's actually fairly easy. That's the easy part. And for doing everything before, all the oceans of the world are no older than 175 million years. The Earth's 4.6 billion years old. So we're seeing like maybe 5% of the history of the earth in the oceans and, or less. And so to build the rest of the history, they use, things called paleomagnetic indicators. So they're magnetic minerals in sediments like magnetite that align with the North Pole. And you can measure the inclination and it tells you what the paleolatitude was. And so you can get the paleolatitude and then it's matching up to geology too. It's just a very, and it's all done on computer programs, but there's a lot of basic science behind it. But I mean, that movie I showed you, that's like decades, it's really centuries of research because geologists have been putting the data together since the 1700s. You know, the fossils and the rocks and the age dating. You have to be able to date the ages of things. So it's the whole science of geology gets put into that.
Okay, I think we have time for about one more question. Does anybody have one? Sure.
We got one here.
I'm sorry if this sounds naive, but if the oceans ever only came, a couple of million years ago, are you saying that the land was all dry before that? And if so, where did the oceans come from?
No, that's a good question. There were oceans since the beginning of the earth, but the ones that we know are new. The Atlantic, the Pacific, the Indian, and the Arctic Oceans. This is one of the big discoveries of plate tectonics in the 1960s, was that the oceans are young. We knew the continents were old because we could age date them, 4 billion year old rocks in the Canadian Shield. But when they started studying the oceans with ships and doing, they were getting samples from ships and measuring the magnetics and everything else. When then the bathymetry, they met with sonar measuring the shape of the ocean bottom. Once they got that information, this whole theory of plate tectonics came together, and it came together in the oceans. But these are just the last 200 million years out of 4.6 billion. And so, but there were oceans before that. And if you look at the other reconstructions I did of Rodinia here, this is all one continent, and then 7/10 of the globe is water. It's still ocean. It's just all been reconstituted, reassembled.
Well, that was a great last question, and thank all of you for being here. And let's give Rich another hand for a fascinating presentation. Thank you so much. Enjoy the rest of your evening and go home safely.
Great questions. Thank you. Yeah.
I do not know.
Right. The sea level was high. Why was that? Because it was a very warm period.